Swayam Prabha. Digital India. Educated India.
Okay, so a quick recap. So last time we basically looked at the quantity which we defined as heat capacity, and we basically found out the expression for the difference between heat capacity at constant pressure and constant volume, and we saw that constant pressure heat capacity is always greater than heat capacity at constant volume. And we also came up with a new concept which is called adiabatic index, which is equal to the ratio of heat capacity at constant pressure and constant volume, right. So, we defined adiabatic index as, which is denoted by gamma as ratio of Cp divided by Cv, and we saw that its value is 5/3 for an ideal monoatomic gas. Okay. And we also looked at a few more things like compressing an ideal gas. So, basically compression of an ideal gas. Ideal gas, right, and we basically saw that we can do it in two ways. One is isothermally, such that when we compress the gas, the temperature of the gas does not change, and the other way is adiabatically, right. So, that the heat exchange is not allowed, right. And the way we did isothermally was we basically put our system in contact with a huge reservoir whose temperature T remains fixed even if there is a small change in a small transfer of heat going back and forth, right. And on the other hand, we in adiabatic process we insulated our system, we removed the reservoir, and we did not allow the heat exchange to happen. Okay. And in this case, basically like I just said, the temperature remained fixed T, which also means for an ideal gas the change in internal energy is 0, right. And we saw that in this case the work done when we compress a gas is given by n kBT times log of Vi by Vf, right. And also we saw that and since we are compressing the gas, Vi is greater than Vf, and this is a positive quantity, which means we are doing work on the system. And also from first law, which is delta U equals delta W plus delta Q, we saw that delta Q is basically just equal to minus of delta W, right. And we also know from ideal gas equation that for an isothermal process, PV is a constant, right, at constant temperature. On the other hand, in an adiabatic process, we said the heat exchange is not allowed, which means delta Q of the system is 0, right. And in this case, we can also see from first law that the change in internal energy is basically equal to the amount of work done on the system, right, since we are compressing the gas. And we derived these two very important relationships, which is T raised to the power T times V raised to the power gamma minus 1 remains constant, and also from ideal gas equation we can see PV gamma also remains constant. Okay. So, these were some important results that we derived in the last class. Okay. So, what we will basically do is we will just try to understand these two relationships little bit more, right. So, basically what we will do is so compression of ideal gas on an indicator diagram. Right. So, remember we have been discussing about this indicator diagram, which is basically a plot between pressure and volume, right, and this is this plane is known as indicator diagram. And we know for an isothermal process, no matter what happens, the product of pressure and volume always remains constant, right. So, for a constant temperature, the P and V inversely scale with each other, and this is how a typical isotherm looks like. Okay, let me draw it in a slightly different way. Okay, this is how an isotherm looks like, right. So, let me call this this is an isotherm. But on the other hand, if we are doing this process adiabatically, the product of P V raised to the power gamma is constant, where gamma now is an adiabatic index, right. And let me do that with red color, and it turns out it looks something like this, right. So, here also the as we increase the volume, pressure goes down, but the slopes are different, right. That is exactly what we will basically try to understand. So, this red line is adiabat. Okay. So, basically what I am trying to say is that for an isotherm, right, PV equals constant, and let us call this constant is some K1, okay, in which case we can write our P equals K1 divided by V, right. And now if you want to evaluate or calculate the slope of this black line at any given point, right. So, what we do is we take the partial derivative of P with respect to V, and this just becomes minus K1 by V squared, right. I am just taking derivative of this with respect to V, and if I substitute K1 from here back into this equation, this is minus PV divided by V squared, and this is minus P divided by V, right. And this is the result for a isotherm, right. But on the other hand, for an adiabat, so for an adiabat, we know that P V raised to the power gamma is a constant, right, and let us call that constant to be K2, right, and I can write P equals K2 divided by V raised to the power gamma, right. And again, if I want to get the slope of this line at any given point, I will take the partial derivative of pressure with respect to volume, right. So, let me do that, del P by del V in this case basically becomes minus gamma K2 divided by V raised to the power gamma plus 1, right. And again, if I substitute this K2 as PV raised to the power gamma, so this becomes minus gamma times PV raised to the power gamma divided by V raised to the power gamma plus 1, and this is minus gamma times P divided by V, right. So, therefore, we can see that the slope of an adiabat is minus gamma times P by V. On the other hand, slope of an isotherm is just minus P by V, right. So, therefore, we can conclude that the slope of an adiabat is basically equal to gamma times slope of an isotherm. Okay. And that is why I drew this in this way, right. So, you can see this red line always at any given point, its slope is always greater than the black line, right. So, this is an important fact concept that we must understand, and this will basically be useful when we will talk about Carnot engine very soon, all right. Okay. So, having said that, so let us now maybe move on to what is known as second law of thermodynamics, right, and let me tell you the reasons why. Okay. So, basically second law of thermodynamics. So, let us maybe quickly highlight some of the limitations that we have in the first law. Okay. So, remember for first law, right. So, first law statement is basically the change in internal energy is equal to the amount of work done on the system or by the system plus amount of heat provided to the system or taken away from the system, right. And also we saw in the last class, for an adiabatic process, right, we forbid the heat exchange, right. So, we put delta Q equal to 0, which implies our delta U is just equal to delta W, and all that tells you is that the amount of work done on the system will be converted into the internal energy of the system, right. But it does not really tell us about the direction in which this process is evolving, right. So, it does not really tell me anything about whether the work is being utilized in increasing the free energy or the free energy is being used to get some work out of the system, right. All it is saying that there is a equality between these two things, all right. So, basically what I am saying is, so the first law gives no information about the way, right, way a thermodynamic system is evolving with time. A thermodynamic system evolves with time, right. It just inherently does not have that knowledge in it, right. And basically I will give you another example, right. So, remember, let us take the similar example again. So, we have this system which is completely insulated, right. So, this system is completely insulated. So, let me draw that schematically this way. So, you have this complete insulation such that the system can't really exchange heat with the surroundings, right. And therefore, and say we are not even doing any work on this system, right. So, this system, the total internal energy just is constant, right, it does not change with time, right. And all it is telling us is that the total energy does not change, but it does not really tell us what will happen inside this system, right. So, I might create a situation where so remember, say this is a collection of gas molecules, right. So, can this happen that spontaneously, so maybe I can denote these by red. So, say is it possible for system to create a situation where these red molecules, which are on average moving faster than the blue molecules, right. So, the blue molecules represent slower moving molecules, which are which basically means it is at lower temperature, right. So, let me just denote this by C, which means it is a colder part of the container, and this is H, which is hot, right. So, can system spontaneously develop a state where half of the container is at higher temperature than the other half of the container, right. The first law just tells us that the total energy does not change, and you can see that this condition still validates this this change in internal, right. So, the total energy internal energy, even though it does not change, but first law does not forbid such a process from happening, right. And we know from our daily experience that this never happens, right. For example, I am sitting in this room. So, the half of room cannot spontaneously heat up with respect to the other half, right. So, the water in my glass cannot really convert into ice and gives that heat energy into the environment, right. So, that spontaneous process cannot happen at all, and first law just has no way of basically forbidding such processes from happening, all right. And so, therefore, we can now come back to the statements of second law, all right, and there are two very important statements of second law of thermodynamics, all right. So, basically two statements of second law, okay. And the first statement is due to Clausius, right, it is known as Clausius's statement, and this goes as follows. So, no process is possible whose only purpose is to transfer heat from colder body to a hotter body. Okay. So, what this means is this is basically driven by our daily observations that such a process is forbidden, right. So, this colder part of this container cannot really keep on getting cooler and cooler, and the hotter part cannot really keep on getting hotter and hotter, right. So, the heat cannot really flow in this direction. So, it just forbids it, and this is basically driven by our daily observation, right. This is what we so the glass of water does not really phase separate into ice and hotter water, right. So, that just never happens. That is, such is the nature of this universe that we are living in, right. So, that is the first statement, and the second statement is due to Kelvin's, it is called Kelvin's statement. Okay. And this means that so this goes as follows. So, this says a complete conversion of heat into work is forbidden, or work is not possible, okay. Okay. Or in other words, or conversion of heat into work can never be 100% efficient. Okay. And we can maybe try to understand it as follows. So, say we have a system which is kept at certain temperature T, and say we design a device which can extract some heat from this body, right. So, let us call it E, which is some kind of engine or device that can do this, and say we are intending to convert all this heat into work, right. So, it is like saying I have this room, and this room has 10 raised to power 23 and even more number of gas molecules which are moving with some kinetic energy, and the total kinetic energy, can I just convert this total kinetic energy into work, right. First law does not really say that, right. So, if I just look at this thing, so the first law only tells you that Q is equal to W, right. So, first law does not really forbid this process. So, it can only equate the energies, it can only talk about the conservation of total energy, right. It cannot really tell us whether that process is forbidden or not forbidden, is it allowed or not allowed, all right. And Kelvin's statement again comes from daily observations that we can't really convert all the kinetic energy of these gas molecules in this room into some useful work, right. So, there is something which is forbidding this thing to happen, all right, and that is where the second law comes into the picture, right. So, it is completely driven by our daily observations, all right. Okay. So, so I already talked about this word which is the efficiency, right. So, I said the conversion of heat into work can never be 100% efficient. So, then the next natural question is, okay, so what is the maximum efficiency that we can extract, right. So, say in this room, say this room has certain joules of kinetic energy, how much work I can extract from that much kinetic energy, right. So, that is the question that we are trying to address, and that is where the Carnot engine comes into the picture, right. So, the next thing that we will do is basically Carnot engine. Okay. And Carnot engine basically is based upon following two postulates, right. So, based upon following postulates. Okay. So, when Carnot came up with the concept of this engine, so he applied these two ideas which again were motivated from a daily observation, right. So, the first idea, the first postulate was the heat can never flow from cold to hot reservoir, okay. So, the heat flow from a cold body to hot body is forbidden, okay, and again this is what we observe all the time, okay. The second is the heat flow stops when two reservoirs are at same temperature, okay. So, when they are at thermodynamic equilibrium, the heat flow cannot happen, right. So, this basically tells us that once we have a system at a fixed temperature, there will be no net heat flow, right. So, the one corner of the room cannot really heat up spontaneously and other corner of the room cannot really cool down spontaneously, even though the total energy of the system is maintained, okay. So, that is not allowed, okay. So, based upon these two postulates, he came up with this concept of Carnot engine, and what we will now try to do is we will try to find out the upper bound of this efficiency with which we can convert heat into work, okay. So, let us see how it goes, right. So, basically okay, so what we start with a reservoir, right, which is a huge system which is kept at certain constant temperature Th, right. There is an engine, there is this mechanical device which can extract certain heat from this reservoir, let us call this engine, okay. And our aim is to convert some of this heat which is in this system, right, into some useful work, and since the efficiency cannot be 100%, we have to dump some amount of heat into another reservoir which is kept at a lower temperature, which is TL, okay. And the reason we are using the word reservoir is because we are assuming that when we remove some heat from this system, the temperature does not change, right. So, it is such a huge system that even if I take out some heat from it, its temperature is maintained and it remains at Th. And similarly, there is another reservoir which is at lower temperature. When I dump some heat into that, it barely changes its temperature, alright. So, that is why these are reservoirs, okay. So, maybe I can write this is a hot reservoir and this is a cold reservoir, okay. And these symbols H and L just means hot, like high temperature and low temperature, okay, alright. So, basically what we are interested in, okay. So, the quantity that we are interested in is the efficiency with which we can convert heat into work, right. So, we can define the efficiency, which is basically, so efficiency is usually defined as output by input, right. So, how much effort we are giving and what is the output we are getting, right. So, the output divided by input, right. And this is usually denoted by symbol eta in Carnot engine in this case, and you can see the output that we are interested in is the work, right, which is W, and the input is basically QH, right. So, that is the input, and so this is basically how we can define the efficiency. Now, okay, so now let us apply first law to this case, right. So, from first law we can see that the work extracted has to be equal to the difference between heat extracted from the hot reservoir minus heat dumped into the cold reservoir, right. So, this is just the first law. So, from first law this W has to be equal to QH minus QL, okay, and we will substitute this here. So, we get eta which is equal to QH minus QL divided by QH, and this is 1 minus QL by QH, okay. So, this is the efficiency, and you can already see that we are subtracting some finite value from 1. So, this efficiency is already less than 1, right. So, the moment we say that we put another reservoir into the system, our efficiency goes down, okay. So, this is clearly eta is less than 1, okay. but we want to write it in a more useful way, right. So, right now this expression of eta is in terms of heats, and heats are like a little bit complicated quantities to make sense of. So, we want to express this efficiency in terms of some state variable, right. So, let us do that. Okay. So, basically expression, okay, maybe I can go to next page. So, expression of eta. Okay. And when we want to express eta in certain state variable, we have to define certain protocol, right. And this is the working protocol that Carnot came up with. So, we have this indicator diagram. So, we have this P, we have V, right, and remember we are operating this engine between two temperatures, right, TH and TL, and we have corresponding isotherms for them. Okay. So maybe I can, okay. So these isotherms, okay, so these are two isotherms, which one isotherm is at higher temperature TH and other isotherm is at lower temperature TL, and there are two adiabats. Okay. So let us connect these lines with two adiabats. Okay. So the black one basically, okay, maybe I can write somewhere. So this is an adiabat, okay, and this is an isotherm. Okay. And let us call these 4 points as A, B, C, D. Okay. So this is A, this is B, this is C, this is D, and the process evolves in this direction. Okay. All right. So we first start with certain pressure and volume. We let, so remember the x-axis is volume. So we let the system expand isothermally while keeping the temperature constant at TH, and then we let the system expand further adiabatically by after removing it from the hot reservoir. Then we compress the system isothermally to decrease its volume, and again we compress the system adiabatically to go back to its initial state, right. And in this cycle there is certain amount of work which will be extracted, and that is basically just given by this area between these four lines, right. So this is the amount of work that we extract, right. So sorry, so this is the amount of work that we can extract. All right. So let us try to understand this. Okay. So like I said, so what we can do is I can maybe draw a schematic of this, right. So basically our process is divided into 4 parts. So one is A to B. Okay. So this is, so first part is A going to B, and like I said, this is an isothermal expansion. Okay, that is the first part. After that we go from B to C, which is an adiabatic expansion. Then we go from C to D, which is again, now the volume is going down. So this is an isothermal compression. All right. And finally we have D to A, which is an adiabatic compression. And the way system works is as follows, right. So and we are assuming that so we are assuming the working substance. So working substance is 1 mole of ideal gas. Okay. So this is an assumption that the working substance is ideal gas. So what we do is, so we have, remember we have this hot reservoir and we have a cold reservoir. So hot reservoir is TH, cold reservoir is TL, and the first step is isothermal expansion, where our system is in contact with this hot reservoir, right, and this is expanding in this way. So, and while it does, it extracts heat QH from the hot reservoir, all right. So, this is what process A to B looks like on the indicator diagram. So, the process B to C is when we remove we isolate this system and expand it adiabatically, right. So, basically we have again this hot and cold reservoir, and what we do is we remove this system from these reservoirs and let it expand, and in this case the temperature of system basically lowers from TH to TL, right. So, and since it is not in contact with reservoir, any reservoir, this is an adiabatic process, all right. So, here the temperature lowers, and then what we do is again we have TH and TL, okay, and now we are talking about C to D, where the volume of the system goes down. So, we put this system in contact with cold reservoir, and this is basically compressing, and the system basically dumps heat QL into the cold reservoir, right, and D to A is further an adiabatic compression. So, we have hot reservoir and we have a cold reservoir, and this system further, so I am drawing this system, okay, maybe I should. So, this is the system. So, we remove it from any of the reservoirs and we compress it further, and since it is an adiabatic compression, the temperature of the system goes from TL to TH, right. So, it heats up, and essentially what we do is we basically go back to this first stage, right, and it is a cyclic process and it keeps on doing this cyclic process, and we are extracting this work out of this system, all right. So, basically let us try to first calculate what is the efficiency if we perform a process in this way, all right. Okay. So, first step, okay, maybe I can draw the indicator diagram again. So, we have two isotherms TL and TH and TL, and we have two adiabats, and the engine is operating in this direction. So, in the first step, which is from A to B, which we know it is an isothermal expansion, right. So, clearly in this case the heat is added into the system, right, and the temperature of the system is maintained at a constant temperature TH, right. So, therefore, the heat added to the system QH will be given by, for 1 mole of ideal gas, R times TH times log of VB by VA, right. So, final volume divided by initial volume, and let us call this equation number 1. And we can see that here, since VB is greater than VA, the QH quantity is also positive, which clearly means heat is added to the system, right. Okay. So, similarly we can go to the next step, which is from B to C, and we know that this is an adiabatic expansion, right. And here clearly in adiabatic process the heat exchange is forbidden, and we know from the last class in this case the relationship is TH times VB raised to the power gamma minus 1 corresponding to this point equals TL times Vc raised to the power gamma minus 1, and this implies I can write my TH by TL ratio as follows. So, this is Vc by Vb raised to the power gamma minus 1, and this is the equation number 2. Okay. And the third step is going from C to D, and this is an isothermal compression. right. So, isothermal compression. And we can do the similar thing as we did here. So, in this case the heat QL, heat exchange, will be given by R times TL times log of Vd divided by Vc, right. And let us call this equation number 3. And we can see that Vd is less than Vc, which implies our QL is negative, and that means the heat is released from the system, right. And this heat is dumped into the cold reservoir, right. So, here the heat is absorbed into the system and here the heat is dumped into the reservoir, right. So, basically this amount of heat released to the cold reservoir. Okay. And again now we can also do the fourth step, which is basically going from D to A, and this is an adiabatic compression, right. And again we can write the relationship as follows. So, TL times Vd raised to the power gamma minus 1 equals Th times Va raised to the power gamma minus 1, right. So, TL times Vd raised to the power gamma minus 1 equals Th times Va raised to the power gamma minus 1, and here I can write the ratio Th by TL, right, the same way we wrote here. So, Th by TL basically becomes Vd divided by Va raised to the power gamma minus 1, and we can call this equation number 4, right. And now what we can do is we can very quickly compare the equation 2 and equation 4. The left hand sides are same. So, therefore, we can very easily see that, okay. So, from equations 2 and 4, so right hand sides are equal. So, therefore, we can write Vc by Vb raised to the power gamma minus 1 equals Vd by Va raised to the power gamma minus 1, or this implies Vc by Vb equals Vd by Va, or I can also write this as Vc by Vd equals Vb by Va. Okay. So, this is what we get from equations 2 and 3, and now what we can do is we can divide equations 1 and 2, right. So, from equations 1 and 3, right. So, equation 1 is the expression for QH and equation 3 is the expression for QL. So, I can clearly see that QL divided by QH is equal to RTL log of, so this is QL Vd by Vc. So, log of Vd by Vc and this thing divided by RTH log of Vb by Va. Okay, and the R cancels out and we are left with TL times log Vd by Vc times divided by Th log Vb by Va, right. But we can see Vc by Vd is equal to Vb by Va, right. So, what I can do is I can switch the numerator and denominator and I can write minus TL log of Vc by Vd divided by Th log of Vb by Va, and I know Vc by Vd equals Vb by Va. So, this cancels out and I am left with negative of TL by Th, right. And we should understand the origin of this negative sign, right. So, it just boils down to the convention, right. So, remember we said that when the heat is released into the reservoir we attain a negative sign, but when heat is absorbed by the system it is a positive sign. Okay. So, what we can do is we can basically just work with the magnitudes and we can explicitly mention the heat absorbed. So, QL is heat dumped into the cold reservoir, QH is heat absorbed by the from the hot reservoir, and if we are careful about our wordings we can get rid of this negative sign, right. So, basically I can rewrite the ratio of heats dumped into the cold reservoir divided by the ratio of heat absorbed from the hot reservoir. In magnitude it is basically just equal to TL divided by TH, and this is an important result, right. So, this is a very important result. Okay. So, therefore, the advantage of having this expression is that now we can go back to the efficiency of the Carnot engine, right. So, therefore, the Carnot efficiency, which is given by the quantity eta, which is 1 minus QL by QH, right, and now I can substitute QL by QH here. So, this is 1 minus TL by TH, okay, and this is a very important expression, right. So, therefore, we end up with two very important results. So, we have the Carnot efficiency of an engine which is operating between a hot reservoir kept at temperature TH and a cold reservoir kept at temperature TL as 1 minus TL by TH. And another important result is that the ratio of heat exchange with the hot and the cold reservoir is basically just proportional to the ratio of those temperatures, right. So, QL by QH equals TL by TH, okay, and these are two very important results that we have obtained after going through the Carnot process, okay. So, clearly we can now see that the efficiency of a Carnot engine can never be equal to 1, right. So, remember, so since TL can never be 0, right. So, we are always subtracting a finite number from 1. So, efficiency is always less than 1, okay. So, maybe I can write it down. So, so the Carnot efficiency is always less than 1, okay. It can never be 100%, and we can very quickly take a very simple example. So, say the temperature of the hot reservoir is kept at 2000 Kelvin, right. This is typically the temperature in our combustion engines and so on, and say the temperature of the cold reservoir is 300 Kelvin, which is typically the room temperature or atmospheric temperature, and if we plug these values here, so we can see that eta is 1 minus 300 divided by 2000, and this comes out to be 0.85, right. So, that means if we have an ideal Carnot engine operating between two temperatures 2000 Kelvin and 300 Kelvin, the maximum efficiency that we can extract out is only 85%, right, and this is the upper theoretical limit on the efficiency that we can extract, okay. But so that is an important point, okay. So, the complete conversion of heat into work is not allowed. We can only convert it up to a maximum theoretical efficiency of 85% for example in this case, okay. And I want to stress another very important point. I want to go back to this indicator diagram. So, remember, I always drew these solid lines, right. So, points A, B, C and D, they are connected with solid lines, and if you remember, the solid lines represent that the process is quasi-static and reversible, right. So, the quantities like quantities like volume, all the thermodynamic quantities like volume, pressure, temperature, they are well defined along these lines, right, and that is possible only if the process is occurring quasi-statically. And when we are dealing with a quasi-static process, that happens by definition very slowly, right, and therefore, what we are talking about is basically we are extracting some work, but over a very long period, right. So, therefore, this engine is in some sense useless because the power output, which is basically the amount of work per unit time, that is basically 0, right. So, basically since Carnot process is reversible and quasi-static, the power output is basically it tends to 0, right. So, we cannot really extract anything useful out of this engine, and this is purely a theoretical framework, okay. And now if we really want to put it into a function, right. So, what we have to do is obviously we have to perform it at faster than what a reversible process requires, right. In which case we will be operating this engine irreversibly, right, over a finite amount of time, in which case we won't be able to join these lines, these points with a solid line, and as a result, as you know, in that case we will be basically wasting lot of heat, right. So, there will be friction. I am not even talking about things like friction and sound and so on, right. And if you think about it, all those real life realities when we put into the engine, they will only contribute to QL, right. So, all the frictional heat or sound and all that will contribute to QL, and that will only reduce the efficiency of this engine, right. So, if we perform this engine irreversibly, we are bound to lose lot of energy in form of heat or sound and light and so on, which will be contributing to QL, and that will lower the efficiency of this engine further, right. So, therefore, this is a theoretical upper limit, and this is allowed only for a reversible engine, right. So, basically what I am saying is, if I have a Carnot engine with an efficiency eta Carnot which is performing irreversibly, that has to be less than a Carnot engine efficiency which is performing reversibly, and we will come back to this concept later on. Okay. So, so having said that, the next thing that we can do is, we can now calculate the amount of work that we are extracting out of this engine, right. So, essentially what we are doing is, we are calculating so we are basically calculating the work that we are extracting out of this engine, and which clearly is the area enclosed between these points A, B, C and D, right. So, that is the work. So, this is the this is the work output, okay, output work, and we are interested in the expression for this work, okay. So, let us do that exercise. So, basically work extracted from I will stress again, from a reversible Carnot engine. Okay. And basically the total work that we will be extracting, that I denoted by a symbol W, that is the amount, that is the total sum of work work in every single step, right. So, basically the W that we are interested in is basically sum of WAB plus WBC plus WCD plus WDA, and maybe I can quickly draw this again. Okay. So, the process A to B is a isothermal process. Sorry, this is TH, this is TL, A, B, C, D. So, we are moving in this direction, right. So, these two are isothermal processes and these two are adiabatic processes, okay. And now we can start from the step 1, which is from A to B, right. And we saw earlier that okay, so since this is an isothermal process, right, so temperature remains constant. So, therefore, the change in internal energy is 0, and therefore, the amount of heat, so therefore, from first law I can write QH plus WAB equal to 0, which implies I can write my WAB as negative of QH, right. And the expression of QH we have already worked out, and this is given by equation 1 here, right. So, therefore, this simply becomes, so which implies I can write my WAB as negative of RTH log of VB by VA. And now you can see, since VB is greater than VA and there is a negative sign, so this work is negative, which means the system is doing work on the surroundings, right. So, therefore, we are extracting work out of the system in this step, okay. So, work extracted or work done by the system, sorry. So, work done by the system, since this is a negative quantity. So, similarly, we can now quickly go to the next isotherm for convenience, right. So, the process C to D, which is another isothermal process, and in this case also since delta U is 0, so I can write my WCD WCD is basically negative of QL, right, and the expression of this QL we have already derived here, right. So, this is negative of R, so the QL is this, so we have to just put a negative sign in front, right. So, therefore, so which implies I can write my WCD as minus of RTL log of VD by VC, right. And here now you can see that since VD, so this is V, this is P, right. So, this is V axis. So, you can see VD is less than VC and there is a negative sign. So, this is a positive quantity, right, and this implies so this basically means the work is done on the system, right, work done on the system. Okay. And now we can do BC, right. This is the adiabatic expansion. So, what is WBC, right. So, by definition we saw that WBC we can write as negative of PdV, where the volume changes from VB to VC, right. So, volume changes from VB to VC, and from the last class if you remember, so we wrote this as CVDT, where now the temperature goes from TH to TL, right. So, TH to TL, and again from the last class we saw this we can write as R divided by gamma minus 1 times TL minus TH, right, and this is for 1 mole of ideal gas. And similarly, now we can write the same equation for the other adiabet, which is from D to A. So, WdA is again the integral starting from TL to TH, right. So, TL to TH CVDT, and this is R divided by gamma minus 1 times TH minus TL, right. So, therefore, the total work is basically WAB plus WBC plus WCD plus WDA, and I can write this as follows. So, this is minus RTH log of VB by VA WBC is plus R divided by gamma minus 1 times TL minus TH minus WCD is RTL log of VD by VC, right, VD by VC plus WDA, which is R divided by gamma minus 1 times TH minus TL, and you can see that these terms cancel out, and I can write this as follows. So, this is minus RTH log of VB by VA, and I can invert this and convert this into positive sign. So, plus RTL log of VC by VD. Okay. And remember we saw that in the Carnot engine so here we saw that VC by VD equals VB by VA, right. So, VC by VD equals VB by VA. So, I can just write it as follows. So, this is R times TL minus TH log of VB by VA. Okay. And you can see that here TL is less than TH, VB is greater than VA. So, this is a negative quantity. Okay. So, maybe I can write this in the next page. So, W maybe I can rewrite in this way. So, this is W equals minus R times TH minus TL log of VB by VA, and since VB by VA is positive, TH minus TL is positive. So, this work done is so this is negative quantity, right, and this implies, and if the net work done is negative, that means the system is doing work on the surroundings, right, and we are extracting this work. So, work done by the system, right, and we are extracting this work, okay, and this is what we were interested in. So, this is the expression for work extracted from a Carnot engine where the operating substance is 1 mole of ideal gas. Okay. So, towards the end we can basically quickly talk about another very interesting and important concept which is known as Carnot refrigerator. Okay. And simply put, Carnot refrigerator is just the Carnot engine. So, by definition this is just the Carnot engine running backwards. Let me explain what I mean by that, right. So, remember again, like in the indicator diagram, so we connected these 4 points A, B, C, D with a solid line and the arrows representing the direction in which this process is evolving. But now since this is a completely reversible process, we can very easily switch the direction of the arrows, right. So, essentially I can draw an indicator diagram which looks like this. So, this is pressure, this is volume, we have 2 isotherms and we have 2 adiabats, and isotherms are at temperature TH and TL, and we have 4 points A, B, C and D, and rather than going in this direction we can reverse the direction of this process, right. And if we do this in the opposite direction, this is a Carnot refrigerator, right, and I can draw this schematic as well. So, we have a hot reservoir, we have a cold reservoir. So, earlier what we were interested in was, so we were extracting certain heat QH from the hot reservoir and converting into work, but now we can reverse it, right. So, our aim is to basically extract heat QL from the cold reservoir, for which obviously we have to do work on the system and as a result a heat QH will be dumped into the hot reservoir, right, and this is a Carnot refrigerator. Okay. And again in this case we can define the equivalent of the efficiency that we defined for Carnot engine as well. Again like so let me denote that as eta star, which is again output divided by input, right, and here the output that we are interested in is QL, right. So, this is what we are interested in. We want to extract heat from the cold reservoir, and the input is the amount of work that we have to do on the system, right. And again from the first law I can write QL divided by the work will basically be QH minus QL, and this I can write as 1 divided by QH minus QL minus 1, right. And since this is still a Carnot engine just running backwards, so the previous results still remains true, right. So, since QH by QL is still equal to TH by TL, so I can write my eta star as follows. So, if I just substitute it here, so this becomes TL divided by TH minus TL, right. And this is a very interesting expression, right, and things are very different right now, right. So, if so clearly we can see, so if TH is equal to 2 times TL, right, so 2 times TL, in this case my quantity which looks like an efficiency, that basically exactly equals to 1, right. So, so that means this is 100%, right, and not only that, if my TH is almost equal to TL, right, in that case you can see that my eta star essentially diverges, right. So, I can have what seemingly infinite efficiency, right. So, infinite, okay. But how do we make sense of it, right. Efficiency can never be more than 100%, right. So, basically it boils down to the statement of the second law, right. So, remember in the second law we said that from the Kelvin statement that the complete conversion of heat into work is not allowed. but there is no statement of the conversion of work into heat. It turns out you can convert work into heat with 100% efficiency, but the second law statement is about conversion of heat into work, right. So, basically this is because so eta star can be greater than 1 because complete conversion of work into heat not forbidden by second law. Second law of thermodynamics. Okay. So, this is an important difference. Okay. In fact, in this case we do not even call it an efficiency. So, I put a star deliberately. So, in this case eta star is often termed as coefficient of performance. Okay. And I can give you a very simple example actually, right. So, say just to make sense of this statement. So, I said complete conversion of heat into work is not allowed, but vice versa is true, right. So, you can convert work into heat, and I can give you a very simple example. Say you have a block of mass and you apply some force on it and do some work on this system, and after some time this block will move here for example, and it will basically come to rest, right, at this point. And while it does that, it will waste all this energy that you have put into the system into heat, sound and so on, right. So, basically so this is on a frictional surface. So, you are basically converting all the work into heat, which is in the form of sound and heat and so on, right. So, therefore, the conversion of work into heat is always allowed, right, that is not against the second law. So, therefore, we do not really call the quantity eta star to be efficiency, but we call it as coefficient of performance of a Carnot engine, alright. So, yeah, so that is all I wanted to cover in this class. So, see you in the next class. Thank you.